we need to sketch an approximate potential energy diagram for dimethylbutane. And the question doesn't tell me which carbons that I'm going to be looking down at. So I'm going to assume carbons 2 and 3. And again, it's an approximate energy diagram. We don't have to be exact. We don't even have to give numbers. We have to give approximate energies. So I'm going to draw my 6 Newman projections. I'm going to do them as small as possible. I'm going to start with an eclipse one. And I'm going to exaggerate my lines so that I don't write on top of my own writing. The front carbon is going to have 1, 2, 3 methyls, so I put it right here, my 3 methyls. The back carbon has 2 hydrogens and 1 methyl. So right now what I'm going to do is that I'm just going to write what I have attached to it. I'm not going to obsess about the energy yet. I have plenty of time for that later. Now I'm going to start from this eclipse and I'm going to rotate 60 degrees at a time. So starting from this eclipse, I get to a staggered conformation in which the methyl in the back, I'm going to rotate. The methyl in the back is going to be right here on the right. The rest of them are going to be hydrogens. Rotate 60 degrees more. And I go to a second eclipse conformation in which the methyl in the back is now at the bottom right here. Rotate 60 degrees more and I go to which conformation? Another staggered conformation. Wait, this is a CH3 on the previous carbon. I made a mistake. I have 3 methyls in the front. This CH3 in the back now is right here in the middle. Rotate 60 degrees more and I'm going to come to an eclipse conformation. Front carbon again has 3 methyls. The methyl that's right here in the middle is going to be eclipsed with this methyl on the bottom right, but that's a left, bottom left. So hydrogen and hydrogen. And I'm running out of space, but one more and then we're good. It's a staggered conformation. And the methyl that's in the bottom left and the back carbon is going to be now in the top left. Alright, so those are my 6 Newman projections. I'm going to count them because I have to have 3 eclipsed and 3 staggered conformations. And remember that you have to go from eclipse to staggered until you get to 6. Now I'm going to actually think about the energy of them. In terms of this one right here, I have 2 groups, 2 big groups, eclipse with each other in this eclipse conformation. This eclipse in the middle, it also has the 2 methyls eclipse with each other. That's going to destabilize the molecule. My third eclipse has the exact same interaction right here. So my 3 eclipse conformations are going to have 0 degrees between the methyls. It really doesn't matter where you get that torsional angle. Those eclipse conformations are going to have, first of all, they're going to be high in energy, and the 3 of them are going to have about the exact same energy. So I'm going to put 3 lines right there. All right, time to go to our staggered, and I have 1, 2, 3 staggered. What I want to do is that I'm going to check for eclipsing interactions between the methyls. So 1, 2 eclipsing interactions, the other methyls on the other side. This one right here, 1, 2, 2 eclipsing interaction, I'm sorry, 2 gauche interactions right here, the other methyls on the other side. This one, the last one, 1, 2. 2 gauche interactions, the methyl on the other side. They seem to have the exact same number of gauge interactions. So I'm going to give the three of them the exact same energy, and I'm going to give them a lower energy because staggered is more stable than eclipsed, always. And now it's a matter of how artistic you are. I'm not very artistic, so I'm going to try my best to make a curve. But the idea of the curve that I'm trying to make is show that the 3 eclipse and the 3 staggered, they have the exact same energy. So this keeps going and going. So this potential energy diagram shows that the eclipse and the staggers, they all have the same energy.